Hey Math 30-1 students, today we are looking at lesson 7.2, transformations of exponential functions. So we're going to start with a starter question. So this is looking back at 7.1. The population of a particular town on July 1st, 2011 was 20,000. If the population decreases, so that's important to know, at an average annual rate of 1.4%, how long will it take for the population to reach 15,300? So this is our y value. This is our a value, our initial. So we're going to use the equation y equals a, 1 minus I to the power of n because it's decreasing. So we know our y value is 15,300, so we're going to put that in. Our a value is 20,000. 1 minus our I value is, you would have to divide this number by 100, and you would get 0.014 to the power of n. Okay, so this is where I can go y1, y2. The window that I would use would be, I'd go from 0 to 20 for my x's, and for my y's, I would go from, as long as you can see the y coordinate, which is 15,300, so 0 to 20,000, going up by 1. And then you would graph this and go second trace number 5, and that would give you an x value of 18.99. So that would round to approximately 19 years. Okay, so this lesson is going back to our transformations. So what we need to remember is that our c is our constant, and the rest, those letters that we've seen before, go back to our transformations unit. For example, the a value is our stretch, our vertical stretch by a factor of a about the x-axis. The b is the horizontal stretch about the y-axis by a factor of, you have to do that reciprocal value, so don't forget to do the reciprocal to get that. And then your k value and your h value are your translations, vertical versus horizontal. So those don't change. So what we just want to remember is what that new form is and that constant. In this case, it is our base. So that, actually in better words, I'll erase that because I feel like it's better to say base. So C is our base. Okay, so remember, order does matter. We have to do our stretches, then our reflections, and then our translations. Okay, so in example number 1, they want us to transform the graph of y equals 4x. So in our case, our c value doesn't change. So there's our c value. It hasn't changed. Don't worry about that. That should remain the same. The base is the same. So they're saying what is happening to the graph of y equals 4 to the power of x when it becomes 4 to the power of negative 2 in brackets x plus 5, and with this minus 3 outside of all of that. State the parameters of a, b, h, and k, and then so we're going to write down what each of those are. For example, a is equal to our value in front of our base, which there is no value in front of 4, so our a value is 1. So if you don't see a value in front of your 4, which in our case is our base, it's 1. Our b value is going to be the reciprocal. So our b value right now is minus 2, but we're going to have to make sure we split that in and do certain things for our transformations. And then our h value in this case is negative 5. And our k value is negative 3, minus 3. Okay, so those are the parameters. Let's talk about SRT, the transformations that occur. So we want to do them in order. For example, we have a horizontal stretch. I'm just going to use abbreviations, but remember when it's an assessment, you should be writing out the whole thing. About the y-axis by a factor of, we have to flip it. So 1 over 2. So don't forget that the negative is not part of that, that horizontal stretch, so don't include that. The negative is for the next part, which is the reflection in the y-axis. And then we have a horizontal translation of 5 units to the right. And we have a vertical translation of 3 units down. Okay, so let's compare the domain, the range, the horizontal asymptote, and the intercepts, and that will really tell us how these transformations are affecting it. So let's split the two. We have the y equals 4 to the power of negative 2, x plus 5, and then minus 3 here, and compare to the original 4 to the power of x. So let's look at the domain first. The domain for the original one would be x such that x is an element of real numbers. So it extends forever left and right, and that would actually be the same for the transformed image. So that would not change. It would still be XER. Range. The range would be y such that y is greater than 0, YER. So we saw that in the previous lesson. And then this one, though, we have y such that y is greater than negative 3, YER. So the reason being is that there's a vertical translation of 3 units down, so that takes that value, that horizontal asymptote, and moves it 3 units down as well. So the horizontal asymptote used to be at y equals 0, but now it's at y equals negative 3, which is why the graph can only exist where it's from negative 3 and up. Now there is an x-intercept there's actually none in this one. So because there is a horizontal asymptote at y equals 0, there is no x-intercepts, right? Now, the reflection, so I just wanted to point out that the reflection along the y-axis doesn't change the domain. So that's something that is not affecting our domain. So that's why there has been no change. The reflection hasn't really affected it whatsoever. Now for the next graph though, we're going to have to find out what the x-intercept is, because this graph, since the horizontal asymptote has moved 3 units down, there will be an x-intercept. So I'm going to take a moment to graph this in my graphing calculator, just to show you how to find that x-intercept. So 4 to the power of, you're writing negative 2 bracket, x plus 5, close the bracket, and then outside the function you have to subtract 3. Okay, so when I graph this, there is an x-intercept right there, so I'm going to have to go second trace number 2, and I'm going to move my cursor to left bound, press enter, right bound, press enter, and enter again. So you should find that there's an x-intercept of negative 5.4 if you round to the nearest tenth. So don't assume, always check. Okay, so we want to write that the x-intercept occurs at negative 5.4 and 0. And then the y-intercept, for the first case, the y-intercept would be at the point 0 and 1. Okay, so that's going to be always occurring if there's no transformation. It's going to be at 0 and 1. Actually, because the reason being there's no value in front of 4, it's a 1 even if you don't see it, and that's your y-intercept. Let's look at the next one. Now, this one, again, we don't want to guess, so we want to use our graphing calculator. So let's go trace, 0, enter. So trace, 0, enter is how you're going to have to do in your calculator. In mine, it's a little slightly different. I'm going to have to press second trace 1, and then press x equals 0, enter. So I get that the value is actually negative 2.99999. So if you rounded, you could say negative 3 if you wanted to. So that is what I'm going to do. So 0 and negative 3. Okay, so as you can see, that vertical translation moves that y-intercept 3 units down, and the x-intercept is being affected by that like movement as well, so that whole graph is moving down, so that's the reason. So you're really seeing that the vertical translation has a lot of effect on the graph. Okay. Oh, and then one more thing, let's do the mapping notation, so that's always important. So the mapping notation would be xy would become, now your x value is being affected by the horizontal stretch, so you would say 1/2 x, and then you'd also have to have a negative in front of it for that reflection in the y-axis. And then we have 5 units to the right, so we're going to say, oh, I just realized it should be actually 5 units to the left. Let's fix that right there. So it should be 5 units to the left, which means that I would have negative 5. And then our y coordinate is only being affected by that vertical translation of 3 units down. So you go y minus 3. Close your brackets. Okay, so double check that it all makes sense. So that's the mapping notation that you would need to include. So mapping notation, very important. Okay, and that kind of gives you a check, and as you can see, I made an error, so I just was able to fix it by doing that mapping notation. So that negative 5 corresponding to going to the left. Example number 2, write each transform function in the form y equals a, c to the power of b, x minus h plus k. So it says for a, that 3 to the power of x, after it's been horizontally stretched by a factor of 1/2, reflected over the x-axis and translated 7 units up. Okay, so let's see how this affects it. So we have a horizontal stretch by a factor of 1/2. We have a reflection over the x-axis. And we have translation of 7 units up. Okay, so what I want to do is I want to write g of x equals, so there's no vertical stretch, so you won't have a value of a in front, so it's going to be 3 to the power of, remember we have to do the reciprocal if it's in the equation, so you're going to have 2x, there's no horizontal translation, so I can just write x. The reflection along the x-axis means that there is going to be a negative in front. So normally then that vertical stretch would be, you'd have a 1. So we don't have to include that, but there should be a negative in front of that. And then finally, we're going 7 units up. So we're going to add 7 to the function. So this is what I'm looking for. B. They're just asking you to rewrite h of x, which is equal to 2 to the power of x with all these changes around it. So all you're doing is pretty much replacing your h with 2, and then you're just doing the power of for this part. Always your bx minus h should be in the exponent part of it. Okay, so we're going to write y equals negative 4 in front. That's your reflection and your stretch. Then you're going to have 2 to the power of your b x minus h, which is 2x minus 3. And then you're going to have plus 5 as your k value. Example number 3, the radioactive element AM is used in household smoke detectors. So the name is AM241, has a half-life of approximately 432 years. So that's that p-value in our exponential growth or decay kind of equation that we made in the previous lesson. So we know the average smoke detector contains 200 of these units. So that's going to be 200 is going to be your initial, your A value. So when we're making our equation, it's going to be y equals A. We can write b to the power of something, or we can write ab to the power of t over p, right? So in this case, we know that y equals our initial is 200. Now, since we're talking about half-life, that's going to be our b value. So we're going to write 1/2 to the power of time, in this case, over our p value, which is 432 years. Okay, so it says, what is the transformed exponential function that models this equation? Well, what we have so far is this is our base, right? So our A value is 200. So we have a vertical stretch of a factor of 200 above the x-axis. So that's what we want to write. And we also have, if you look at this, guys, you want to write it in front of t. We can rewrite this as 1 over 432 times t. The reason being is then this will look like your b. So your b value is your horizontal stretch by a factor of 432, because you have to do the reciprocal to actually get that value. Okay, so how does this, so that's all we had to do for A. For B, they're asking us to identify how each of the parameters of the function relates to the transformed graph. So we know that the vertical stretch relates to the initial amount or average smoke detector amount. And our vertical stretch refers to our half-life. Or a horizontal stretch, it should be horizontal stretch, or horizontal stretch relates to the half-life years. And that's all we have to do for B. Example number 4. The estimated population of a city in 2011 was 35,000, with an annual rate of increase of about 2.4%. So that is, we would have to change this right away to a decimal by dividing by 100, and we get 0.024. We also know that this is our A value, it's our initial amount, and then we're going to use the 2011 for our N and then find our future amount. So how many years after 2011 are you? Okay, so what is the growth factor for this city? Well, that in this case, we're going to have to find out our B value. So our B value, so for A, the growth value is just going to be doing that in the equation. We'll write out the whole equation. I'll just show you where it is and point out to it where that growth rate is. It's going to be 1 plus I to the power of n. So you're going to have y equals, A is 35,000. 1 plus your interest rate. In this case, it's your percentage of increase, your annual rate of increase in the population. We wrote it as 0.024 to the power of n. So we're just going to combine these two numbers together. Y equals 35,000, 1.024 to the power of n. This is your growth rate, your growth factor. Okay, so the 1.024 is your growth factor. B, they want us to graph this. They want us to graph the city from 2011 to 2021. So let's start off from 2011 then, our initial. And then we'll go up to all the way to 2021 here. We know we have to go up to, it says, we're starting at 35,000 and we're actually growing from there. So we should go higher than that. So I'm going to go up to, let's go up to 50,000. Let's try 50,000 for your Y value. This is your N value. Be consistent with the letters. So I found out that my scale is going up by 5,000. So all I did was I took 50,000 divided by 10. So that's what tells me what I should be doing here. Okay. And then this is just going up by year. This will be 2012, 2013, 14, 15, 16, 17, 18, 19, 20, 21. Okay, so this is a 10-year span. So we want to graph this. So we know initially, just by looking at the equation, that this is our y-intercept. So we're starting off at 35,000, plotting a point. We're actually increasing from there. So to get a better picture, I'm going to graph this into my graphing calculator. Change the window to make sense. So clear whatever you have there and then write in your 35,000. We have 1.024 to the power of x instead of n. Your window, we're going to use the same window we have. We're going to go from, in this case, this is going to be how many years after 2011 is it? So I'm going to go from 0 to 10, because from 2011 to 2021, that's 10 years. And then for our y values, we're going from 0 to 50,000. Graph it. And then you can go to second graph. I don't know why it's so weird like that. But you can then plot a few values. So I just want a better kind of image. So that's why I'm plotting a few years after that. So let's do... I know at the year 2021, I'm going to have about 57,000, so slightly higher than that. So I don't want to go higher than 50,000. So let's go up to, at the time of 15 years. So let's do, we have x up to 10, right? So let's do at the 10-year span, meaning at 2021, we should have 44,367. So at that 10-year span, 44,000 would be approximately here. And then you're just trying to draw that kind of exponential function, that growing quickly kind of curve. So it should not look linear. That's what's really important, is don't make it look linear, curve it so it's exponential. Okay, so once we graph the function from 2011 to 2021, C is asking us for use your graph to estimate the population in 2016. Well, in 2016, we could, if we really wanted to, we could find that out. So 2012, 13, 14, 15, 16, we know that we're looking at this as 2016. But to be more specific, what we should do is go to our equation and write it in, right? So if we were to write in our equation, we have y equals 35,000, 1.024 to the power of n. Well, 2016, if you subtract 2011, your starting amount, you get 5 years. So there's been 5 years since your initial $35,000 or 35,000 people have been in this place. So let's find out what y value, what is the population after 5 years. So 35,000 in our calculator, 1.024 to the power of 5. You should get that there are, if you round properly, it should be 39,406 people. And this is approximately. And then finally here it says, discussion. The graph of an exponential function in the form of y equals c to the power of x does not have an x-intercept. Explain why this occurs using an example of your own. Well, because there's a horizontal asymptote. There is a horizontal asymptote at the x-axis. So an example is from our previous lesson. We had 3 to the power of x. When we graphed it, it looked like that, and it did not touch the y equals 0 line. What parameters of an exponential function affect the x-intercept of the graph of the function? Well, you could play around with this and see that it's both your base and your h value, your horizontal translation, that affect the x-intercept. So the base is kind of like your C or B, depending on what form we're looking at, and then your H is that horizontal translation. And then finally it says, what parameters of an exponential function affect the y-intercept of the graph of the function? So what affects the y-intercept? Well, your A, meaning your vertical stretch, and the k value. Okay, so the a value is your vertical stretch, your k value is your vertical translation. Both of those would affect your y-intercept. You could always play around with it, and you could see that it does actually affect your answer. Okay, so that's it for lesson 7.1.